Welcome back to the next video, everybody. Today, we are finally going to start looking at examples of group schemes. Okay, so the setup is that G equals spec A will be an affine R scheme. R is some ring. Okay, we've seen that to give G an R group structure, it suffices to give a group structure on the functor from schemes over R to sets given by send T to the T valued points of G of T, which remember is the R scheme homomorphisms or morphisms, if you like, from T to G. I don't actually have to construct the multiplication map M or epsilon or the inv map that give the commuting associativity, unity, and inverse diagrams, recall, because you can recover M, for example, as the composition of the projections PR sub 1 and PR sub 2, the projection maps, in the group law for the G cross G valued points of G. And you can similarly recover just epsilon and M in the same way from the S valued and G valued points of G respectively, using just by kind of considering the diagrams for unity and inverses. Provided you've already recovered M. Okay, and so it really is enough kind of just to give G of T, make G of T a group in a functorial way for each T. That's really all you have to do. Okay, a little bit more setup. Since G is affine, we can usually assume T is affine because we will be working with certain classes of affine morphisms, usually finite morphisms. Okay, in other words, we can usually write T equals spec B for some R algebra B. Okay, and then when this is the case, like when we're allowed to do this, we'll define G of B to be just G of T. And we'll say G of T, we'll think of G of T as the R algebra homomorphisms from A to B using the equivalence of categories discussed a few videos ago. Remember, affine schemes over R are categorically equivalent to R algebras. Okay, and so really to make G an R group, it's actually enough to make the map that sends B to homomorphisms from A to B a functor from R algebras to groups. Okay, so that's a kind of a ring theoretic way of thinking about what we have to do rather than a scheme theoretic way. And the co-multiplication M tilde from A to A tensor A over R is then obtained as the composition in the group, homomorphisms from A to A tensor A over R, of the tilde of the first projection with the tilde of the second projection. I mean, again, that's what you expect to happen, right? I mean, this is just the ring theoretic version of what happens when you're dealing with the schemes. Okay, so we'll look at two examples of group schemes today, and we'll look at some more tomorrow. First is the additive group, G sub A. We'll let R be a commutative unital ring, and we'll set G sub A to be spec of R adjoin U, where U is to be viewed as an indeterminate here, like a variable. If B is a commutative R algebra, the map from R algebra homomorphisms from R adjoin U to B, given by evaluation, so you send F to F evaluated at U, is very easily seen to be an isomorphism of R algebras. And so you find that G sub A is an R group via the additive group structure on B, as B varies. So in other words, we are able to put a group structure on G of B in a natural way, categorically speaking, as B varies. And so that's enough by what we just discussed. If you want the co-multiplication M tilde, it's just M tilde of U is U tensor 1 plus 1 tensor U, but that's exactly what we discussed above. And then you calculate that epsilon tilde of U is 0 and inf tilde of U is negative U, which is exactly what you would expect to happen since we're working with an additive group structure here. So I'll let you work these out yourself. Okay. I can be a little bit more general with this example. If M is an R module and I let A be sim of M over R, then the R algebra homomorphisms from A to B are the same as the R module homomorphisms from M to B. And this is a commutative additive group under addition for each R algebra B, of course, right? And so spec A is a commutative R group here again, but if you take M to be RU, the free R module on one generator, you just recover G sub A, okay? Because like sim M R can be thought of as like, it can be loosely thought of as like the polynomial ring over R in a number of generators, or in a number of variables equal to the number of generators of M as an R module. So we only have one, right? And so we get RU. Okay, second example, multiplicative group, G sub M this time. This time we'll let G sub M be spec of R adjoin U and U inverse. And so if B is an R algebra, the evaluation map, again, this sends F to F of U, identifies the R algebra maps from R adjoin U, U inverse to B with B cross. Okay, so the units in B. And so G of M is an R group. And M tilde of U this time is the product of U tensor 1 with 1 tensor U, like you'd expect, because we're working with a multiplicative group here, a multiplicative group structure. Epsilon tilde of U, what do you think that's going to be? It's going to be 1, right? That's supposed to represent like the identity here. Inf tilde of U, of course, it's going to be U inverse, right? This is supposed to be like the inverse map, right? And so all of this is as expected. And so we'll look at more examples next time, like the general linear group and the roots of unity and stuff like that. And so I'll see you tomorrow, and thanks for watching.